Hi, and welcome back again to Discrete Mathematics. The title of this lecture is Syntax and Semantics for Arithmetic Expressions. So in this lecture, we're going to pull a lot of stuff together to the point that we're actually able to build our own interesting language, a language of arithmetic expressions. Expressions like x plus y times 2 minus 5. Okay, we're going to specify a syntax for the space of all such expressions with a limited number of operators. We're going to define interpretations for the variables that can appear in such expressions. And we're going to define an evaluation function that, given any expression and an interpretation that tells us what the variables in that expression mean, we'll be able to reduce that expression to its meaning in the form of a natural number represented as a value of type nat in Lean. This is really interesting and it's really important because it's really the last step before we can specify a syntax and semantics for Boolean expressions, and thus for the language that we call propositional logic. And that will take us to the next major topic of this course, which is logic and proof, starting with propositional logic, where we don't actually need a concept of proofs, and then ultimately transitioning to predicate logic, the language of everyday mathematics and computer science, where in fact we will need the concept of proofs because we won't be able to define the truth of a function by the use of a simple evaluation function. So that's where we're going. So here's the agenda for today's lecture. We're going to start with a fairly extensive review of trees and implement a variety of tree structures in Lean so that you are reminded of and see more examples of how trees can be specified and functions that consume trees and return values about those trees can be defined, typically using recursion. It's important to have a good intuitive grasp of trees and recursive functions that do things with trees because, in fact, expressions in most formal languages, like a language of arithmetic expressions, the language of propositional logic, or even Python, Java, or C++, expressions or programs in such language are structured as trees. Expression trees or program trees. So we will review thoroughly the notion of trees, and then we'll transition to a comprehensive presentation of a language of arithmetic expression trees. And again, as I said, a notion of interpretations for the variable expressions that can appear in such trees, and an evaluation function that, when given any such expression tree and an interpretation for the variables in that tree, essentially reduces that expression tree to what it means in the form of a single natural number. So a key concept, or several key concepts really throughout this lecture, are inductive data definitions to define trees, and then recursive functions to consume trees and essentially traverse their structures, summing up or doing other computations with the values that appear in such trees. Okay, so we're going to hop on over to VS Code now. So crank up your VS Code environment, pause the video, and come back when you're ready to go. Good. Here we are in VS Code. Thank you for continuing with the lecture. So here's my source directory. You see I've added a new subdirectory called old. I keep some old files in there that I've developed to put these lectures together. Here's my Scratch subdirectory. You see now that these two subdirectories are on separate lines rather than just coming after the source directory here. But otherwise things are the way they were when we left. So what we're going to do for the rest of this lecture is to create two files. The first is going to be called trees.lean. So let's go ahead and create that file now within the Scratch directory. So what I did is right-click, New File, and then trees.lean. Okay. Down here in the lower right, you can see that VS Code detected that we're editing a lean file rather than some other kind of file. It connects this file to the lean analyzer on the back end, and we're good to go. Right. So our agenda here is to do a kind of a review of trees, some of which we talked about previously. In one case, very early in the semester, we looked at implementing a tree abstraction in Lean. We'll do that again. And we'll go through a set of examples of trees just to really help you think about inductive definitions of different kinds of tree structures. And the definition of functions that take trees as arguments and pull them apart to do things with them. Like, for example, counting up the number of nodes in a tree is a classic example of a task that is well handled by a recursive algorithm. An empty tree has no nodes in it. A non-empty tree is a node, so there's one plus two subtrees, each of which could either be empty, contributing 0, so you have a total of one node in that case, or non-empty subtrees in which the number of nodes in the overall tree is 1 for the top level node, plus the number of nodes in the left subtree, plus the number of nodes in the right subtree, and that's how it works. Okay, so we'll put all that together. So the first example that we went over in this class, and if you see me looking down here, it's because I'm looking at some notes that I've put together. The first example that we looked at in this class is the idea that we can use a tree of names of people to represent ancestry. So let's go ahead and kind of revisit that and think about it. Think about how to implement it and see how to implement that abstraction in the logic of the Lean prover. So we're going to represent the set of all possible ancestry trees, trees of nodes, nodes with names in them, if you will, in the following way. We'll define an inductive data type, and we'll call it, ancestry tree. How about just ancestry to keep it short? And we're defining essentially a new type of object that we'll think of as an ancestry tree. And an ancestry tree, as we indicated before, we'll assume can either be empty, representing nobody and no ancestry at all. Okay, so empty we think of as a term or a constructor, really, a parameter-free, constant constructor for a value of type ancestry. So we'll be explicit here and indicate that empty is type ancestry. It's optional, but we'll put it in just so that our logic is clearer. Okay, so an ancestry tree is either an empty tree, an empty ancestry tree, or it's a person tree. And a person tree has some arguments. Okay, it has some contents, some components, if you will. Think of it as a person record, if you're familiar with the term record from other classes in computing or from, concepts of databases. Essentially, it's a row of data items, a tuple, if you will. So person has a name of type string, and string is a type already provided by the Lean environment. And a person has a mother ancestry tree and a father ancestry tree, and we will model those as ancestry trees. And that's where the circularity is, right? So a tree can be empty, or it can be a person like Kevin with a mother tree and a father tree or subtree. Okay, my mother subtree could be empty, my father subtree could be empty, in which case we have a tree with just me, not representing my ancestry any further back. Or a tree could be a person tree with me at the root, and then a Mary tree for my mother and a Bill tree for my father, and maybe the subtrees of those trees are empty or not empty. Okay, so that's how these inductive data definitions work. This circularity, wherein we define a type partly in terms of smaller objects of the same type, that's the essence of an inductive data type definition. Okay, so that's all we need to say to define an infinite set of possible trees of. You can think of them as trees of strings if you want. Okay, so when we define a type like this, it's often really very, very useful to build some examples of data values of the type that we've just defined to get comfortable that we've actually kind of got our definition right. So to that end, what I'd like to do is I'd like to introduce a new file into our Scratch directory called trees_test.lean. Okay. And in the first line of trees_test.lean, what we'll do is we will include the definitions from, and this is a little bit different than the notation you use in your shell, from the same directory and the file called, I'm sorry, it's not, pardon me, it's not include, it's import. So we will import into the definitions from, in the same directory, trees.lean, into trees_test.lean. Okay. So now within trees.lean, within this file, trees_test.lean, we can use the definitions that come from trees.lean. So let's define just one example of an ancestry tree. I'll call it the Kevin tree, okay, the Kevin ancestry tree. And the question is, well, what kind of tree am I going to define? Well, I only have really two choices. And to see what our choices are, I could flip back and forth between these two files. But let's make some more room on our screen by closing out the project browser. Let's go to the View command and Editor Layout and select Split Right. Okay, now select the right browser and let's visit the trees test.lean file over here. Okay, it's fine. So we have trees test.left and our ancestry tree definition on the right. Okay, so now here we are. I need to define Kevin tree, and I have two possible forms of a tree. It can either be empty, okay, so it can be ancestry.empty. Let's go ahead and open Ancestry here so we don't have to type ancestry dot before everything. Actually, that's a bad idea. That's a bad idea because we're going to define some other types of trees that also have empty nodes in the same file. So we don't want ambiguity. So we'll just leave it like this. So we'll say ancestry.empty. Okay, so that's an empty tree, but that's not what I want to represent here. I don't want the Kevin tree to be empty. I want it to represent a person, namely myself. So we'll say ancestry.person instead of empty. And now we need to give the arguments to this constructor. Okay, so we need, and I'm going to list the arguments on separate lines underneath the constructor name so that we can see the three arguments that are really needed here. So they are a name of type string and then two values of type ancestry, so two smaller trees. Right? And so the first argument here, and sorry to have to scroll back and forth, but is my name. So that's a string. So I'll put that there. There's argument number 1. Now arguments number 2 and number 3 are both going to be subtrees. So I find it very convenient to put pairs of parentheses with underscores where I intend to put more elaborate arguments. And Lean understands these underscores as placeholders for a value that's going to come, and it will even tell you what type of value needs to go into that placeholder, because of course it knows from the type of the person constructor that its second and third arguments need to be ancestry tree. So here and here, you see Lean tells you what's missing is an ancestry tree. Okay, so we are defining a big ancestry tree for Kevin with two smaller ancestry trees as its subtrees. Now each of these, of course, can either be empty or a larger ancestry tree. So here I could put ancestry.empty, and that would be a correct form of subtree. And we could do that in both places here, like that, okay? And so there's a tree that just represents me and no further information about, my mother or my father. But we could have put larger trees here instead of empty trees. So let's go ahead and do that. Instead of ancestry.empty, I'll put ancestry.person here. And of course, that constructor takes 3 arguments, a string. So I'll put Mary, that's not really my mother's name. And I need two smaller trees because those are the second and third arguments to the ancestry.person constructor. Okay, and I'm actually going to leave those just empty, just like that for now, and go ahead and let's go ahead and represent my a subtree of the big tree for my father. We'll change this to ancestry.person, and now I'll leave some space to put in the new, I'm going to put the name Bill here, that actually is my dad's name, and 2 smaller subtrees, either of which could either be empty or a larger tree. And in this case, I don't want to take the tree any further, and so what we're going to put here and in all of these other placeholders is ancestry.empty. So I'm going to select and copy and paste that into these nodes here, and now you get the idea. If I really wanted to represent my grandparents here, well, instead of ancestry.empty for my mother's mother, I would change this to ancestry.person and add, my grandmother's name here and subtrees for her. But that's not what I want to do. I just want to end this tree at this current depth. Okay, so here on the right-hand panel, I have my type definition. In the left-hand panel, I have a test file to test the definitions in my trees file. And I've created I've imported the definitions from the current directory trees.lean file. That's this one right here. And I've created one value bound to this identifier, Kevin tree, of type ancestry, built by applying the person constructor to arguments of the right kind. Okay, and the arguments include, among other things, smaller trees of the same kind, and that's that inductiveness that makes computer science so cool. It's where recursion and induction come into play. Okay, so good. Okay, now I'm going to go back over to my trees.lean file, and now imagine that I want a simple function that takes an ancestry tree as an argument and does nothing other than count up the number of people who are represented in that tree. So in this tree that I'm looking at, the Kevin tree, there are 3 people, Kevin, Mary, and Bill. Okay, so let's define a function called, ancestry count. How about that? Ancestry_count. That'll be the name of my function. And it's a function that takes an ancestry tree as an argument and returns a natural number, either 0 or 1 or 2 or 3, whatever the number of nodes is in the tree. It'll never be negative, so we don't need to use, a more general integer type here. We can use a natural number type, which is a type of values from 0 on up. So the idea then is that ancestry count is a function that takes a value of type ancestry as an argument, and that processes that argument and returns a value of type nat to represent the number of values in that tree. And the way that we're going to define how this function works is by case analysis. We're going to look at 2 cases. What if the tree that we're given, let's call it, T. What if the ancestry tree argument that we're given, let's call it T, is the empty tree? Well, that's one case. And in that case, it's pretty easy to see that the correct value to return is 0, because no people are represented in the empty tree. Okay, but the only other possibility is that the tree that we're given is a person tree. There are no other constructors for ancestry objects. There's no other way to build an object of type ancestry except by using one of these 2 constructors. That's part of the semantics of inductive data type definitions, okay? That the set of values of a type is the set of all values that can be built by applying the available constructors any finite number of times. And there are no other values of the given type, okay? So we say that the values defined by a type are the values spanned by finite numbers of applications of the defined constructors. Okay. So there's really only two cases here, and I'll just write them like this. In one case, the tree is empty, so we'll, if the tree that we're given as an argument is the ancestry.empty tree, we'll return 0. Otherwise, what? Well, whenever we have a constructor expression in this sort of case analysis with at least one argument, then we need to use parentheses, okay? So I'm starting here with parentheses, and the idea is if the tree that we're given was built by the ancestry.person constructor, as this tree was, for example, but not this tree, okay, then that ancestry person constructor must have been applied to 3 arguments. A name, let's call it, I don't know, N. A left subtree for the mother, let's call it M. And a right subtree for the father, let's call it F. We can use any identifiers we want there for in place of N, M, and F, as long as they're not already used somewhere else in our program. We could have used P, Q, and R, or hello, goodbye, lean. It doesn't matter what identifiers you use there, but these identifiers become temporarily bound to the components of the argument that has been passed to us. If the tree is not empty, then it must have been constructed by applying the person constructor to 3 arguments. And here, we're just giving names to them, just in the same way that we would give names to the arguments to any old function. Okay? So, in that case, what's the number of people in the tree? And this is where that recursive way of thinking comes into place. And the key is you don't want to kind of think about unfolding the tree and all of its subtrees and all of their subtrees all the way down. You just want to think recursively, okay? The number of persons in a non-empty tree is 1 for the person at the top of the tree, plus the number of people in whatever left subtree you've got, plus the number of people in whatever right subtree you've got. Okay, so it's 1 plus something else. It's 1 plus the, it's 1 plus the number of people in the left subtree. Okay, that's going to be a natural number, plus the number of people in the right subtree. So let's actually put this down on the next line and even put these arguments on separate lines like this. So the number of people in a non-empty tree is 1 plus, and what we want here is an expression for the number of people in the left subtree. Well, how can we compute the number of people in the left subtree? Well, we apply this function ancestry count that we're in the middle of defining, because given a subtree, given a tree, it returns the number of people. And so that is so cool. All we have to say here is ancestry count M for the mother subtree on the left, and ancestry count F for to count up the number of nodes in the right subtree for the father. And so that is a general purpose function for counting up the number of people, names, in an arbitrarily large ancestry tree. So now let's go back over to our test file and let's evaluate the application of ancestry count to Kevin tree. And what do we expect the answer to be? Well, 1 plus 1 in the left subtree plus 1 in the right subtree. That's 1 plus 1 plus 1 is 3. So we expect the answer here to be 3. And we'll say Kevin tree. And the question now is, do we get the right answer? And in fact, if you hover over this eval, so you don't have to open up the info view, there's the result right there, and it's 3. Okay, so this is a beautiful little simple example in which we define this very, very cool data structure, right? This class or set of objects of this tree of string type, which we're using to represent Ancestry, but we kind of start to forget about the use for this abstraction. It's really just representing a tree of string names, and a recursive function that counts up the number of non-empty nodes in an arbitrarily large tree of this type. Very cool. Okay, good. So let's. I'm going to let me say at this point you should, if you haven't been working in Lean and following along and typing all of this stuff in, go ahead and pause your video right now and type all of this stuff in. There's enormous benefit to just typing it in and developing muscle memory for the syntactic details of Lean and to give your brain a way to think about what's really going on. Okay, really think about everything that you're typing. What does each expression mean? Why is the number of objects in a non-empty tree 1? Well, that's for the parent node, plus this procedure applied, or this function applied to each of the left and right subtrees. Does this function actually give the right answer for an empty tree? Well, we can go try that. Okay, so we'll apply ancestry count to ancestry.empty. Okay, that's an empty tree. And if we hover over here, sure enough, it's 0. If I had a tree with a top level node with 2 empty subtrees, well, that would only contain 1 name, and that 1 would be the result of adding 1 plus 0 for this empty tree, plus 0 for this empty tree, and that would give us the 1 that we would expect. Okay? So one of the things that you want to do is you want to begin to think recursively in this class. You want to say, okay, this big object of a certain type is built up of some stuff plus some smaller objects of the same type. So to compute a result for the whole tree, I'll compute a result for the part that's not a smaller piece of a smaller object of the same type, and I'll compute part of the answer by recursively analyzing one of the smaller pieces and recursively analyzing each of the smaller objects of the same type, and then I'll combine all those answers together. So here I compute 1 to count the number of names in a single non-empty node, plus the number of nodes in the left subtree, plus the number of nodes in the right subtree. I compute these 3 partial results, 1 for the top level node, 1 for the left subtree, 1 for the right subtree, and then I combine those partial results using addition in this case to compute a result for the overall tree. And that's my answer. Okay. Awesome. Okay, so the second example, actually, okay, so let me finish marking this. So this is Ancestry as a tree of strings. And we'll put a little comment in here that says, count number of people in tree. Okay, and now what I was saying before, please, is that if you haven't typed all this stuff in, go ahead and do it now and think about it. Just pause your video, get caught up, think about why this works. Maybe even do a few other experiments of your own over here. Make one of these subtrees a non-empty subtree rather than an empty subtree, and then reanalyze the number of nodes in the tree. Do some experiments, play around with this stuff. It's a great and really important way to, really familiarize yourself with these very, very important and really quite deep and interesting ideas. Good. Okay, so now we go on to our second example, and our second example as discussed informally in earlier lectures, but never really quite formalized, was the idea of a file system as a kind of a tree of files. Okay, so file system is a tree of files. So once again, we're going to define a data type that's going to allow us to represent a tree of files. And we'll define some recursive functions that, given a file system, the object as an argument, return some interesting results, like how many files are in a directory or how many files are in a complete file system. Okay. And so the way that we defined a file system earlier was by saying that a file is a kind of an object that can be either a data file with some contents. So we'll have a constructor called data to construct a representation of a data file, and that constructor will take an argument, contents of type string. And we can think of, data followed by some arbitrarily long string as representing a data file with that string as as the contents of the file. So we modeled a file as either a data file or as a directory file, and I'll just call that dir here. And a directory file, we forgot something. A data file has a name of type string and some contents. Good. A directory file also has a name, which we will model as a string. And instead of some data contents, instead of just a string, it contained a list of files. So we will call the contents of directory contents, but it's not going to be a string now. It's going to be a list of files. And here we're actually going to use a list type builder that Lean provides. Remember, a type builder is not exactly a type. It's a kind of a polymorphic type. It's called list. And we give it another type as an argument, and this type represents the type of lists of objects of this kind. Okay, so our data type then, our file data type, is as follows. A file is either a data file with a name and some contents, that some string representing the contents of that file, or it's a directory with a name and a list of files as its contents. And I'll show you how to use the list of whatever data type here shortly. So let's take our comment here and put it at the top here. And we will take this comment here just as a kind of textual separator in our definition files. And we'll do some testing of our file data type. Okay, so for example, let's represent something that looks like one of the file systems we talked about a couple of lectures ago. I'll define root dir. Okay, I'll use an underscore here. I'll define root dir to be an object of this file type. Okay, I'm being explicit here rather than letting Lean figure out what the type is going to be. I'm going to say root dir is going to be an object of type file, and in particular, it's going to be not a data file, but it's going to be a directory file. So this will be file.dir along with some arguments, a name, and if I'm representing the root directory of some machine, what's a good name for that directory file? Well, slash is a good name for that directory file. And in addition to having a name, the directory also has a list of smaller files as its contents. And so what we need for the second argument is a list of files. Lean provides a nice square bracket notation for lists where elements of the lists within square brackets are separated by commas. So I'm going to open this up, split the beginning and end list across several lines. But note that we've already got a representation of an empty root directory here. We've got a directory file called / with no files in it. So how many files are there total here? Well, there's one, right? There's one for the root directory and none for the content directories. So before we go any further, why don't you take a minute and see if you can find, if you can define a function here that counts up the number of files in a given file system. Okay, so let's call it. We're gonna call this du. Okay, and that's actually a command on most Unix systems that counts up the number of files and the number of bytes of storage that are consumed by a set of files within a directory and all of its subdirectories. So we'll name our function after the Unix command for disk usage, or du. And this will be a command that takes a file as an argument. A file, again, can be a directory or a data file. And if it's a directory, it can contain 0 or more other files. And that returns, let's say, a natural number. And this will just be a count of the number of files in the given file system. So take a minute and see if you can write the rest of this code. Pause your video, give it a try, and then come back and we'll finish it off. Welcome back. Okay, so once again, we're going to define this function du by cases. And there's really just two cases here. Du takes one argument, a file, and a file can only come in one of two forms. Either it's a data file with a name and some contents, or it's a directory file with a name and some contents of a different type. So in the first case, the argument to the function, and we need to put this expression in parentheses, file.data has a name, we'll call it n, and some contents, we'll call it c. Okay. In this case, we're going to ignore the contents and just count 1 for the data file. Right? If you give me a data file and you ask me how many files are there, well, there's 1. So I return 1 as our, what you can think of as the base case for our recursive definition. If the file is not a data file, then it's a directory file. So there's our parentheses, file.dir. If we're given a directory, well, that has a name and it has some contents. We'll call it C. But now the contents is a list of files, right? And so in this case, how many files are there? Well, there's 1 for the directory file itself, plus, well, here we run into a little problem because we don't know how to deal with this list of files that we're given. Okay, so what can we do right here? Well, a great thing to do in this case, and we're not going to try to solve this problem right now here, is to put in a stub. A stub. So a stub is an underscore in Lean, and it represents a place where we need to fill in the rest of a definition that we don't know how to fill in right now. So or that we're not willing to fill in right now because we have more important things to do. Maybe we fill it in later. Okay, so the idea is somehow or other we need to fill in this stub. And what is it going to do? Well, it's going to sum up the number of files in each of the files in the list, and it's going to do that by applying du to each of the files in this list of files. Now, some of those files might be data files, in which case you get back the number 1 for each of them. But if one of these files is a directory file, then it may have subdirectories, and they may have subdirectories, and so on and so forth. So a lot of work could actually be taken care of right here. Okay, so we're going to leave this function not fully defined at this point. Lean tells us some information about what is available and what's needed at this point in our code, and it's actually very useful. Okay, so let's take a look at what Lean is telling us. What can we assume at this point? What we can assume at a stub or at a hole, this is called really a hole in our code. What we can assume at this point is that du is a function from file to nat. And so we can apply that function recursively here because it's available as a definition in the context surrounding this hole. We can also assume that, we can also assume that n is a string. Where does that assumption come from? It comes from right here. Okay, so we've been given a file that's not a data file, so it's a directory file. The directory file must have been built by applying file.dir to some string name and some list here. I'll change this to L. Okay, file.dir must have been, the dir constructor must have been applied to a name, we'll call that n, and a list of files that here we're calling L. So at this point in our code, the assumptions that are valid are that we have a function that we can use called du, and it can be applied recursively if we need to. We have a string n, and we have a list of files L. And in the context of those definitions, of those assumptions, what we need to compute is a natural number. In other words, whatever expression we put here can be built up using du, n, and L, but needs to reduce to a natural number. And so the idea then is if we're given a directory file, the answer that we're going to return is 1 for the directory file, plus a natural number that represents the number of files inside of that directory and inside of any subdirectories and subdirectories and subdirectories all the way down. Okay, very cool. So you might want to start to hover over underscores in your code, even leave underscores or holes in your code where you're not quite ready to fill in. And then what's really cool is that because Lean is strongly and statically typed, you have a whole bunch of information about what information is available to use at that point and what kind of value needs to be produced by the expression that you use to fill in that hole. Okay. What you need is a natural number here. Okay. You could stub this out by saying 0, that's a natural number, and now your code will compile. It doesn't give you the right answer. It's better to leave an underscore here to indicate that really you haven't quite finished off this definition. Okay. So now if I come over here and try to apply this du function, I'm going to have a problem if we try to evaluate the application of du, this function, to root dir. Let's see what happens. We get a little bit of an error, and the error message says you're trying to evaluate sorry. Here's another way of representing a whole. You say sorry, and so you're saying the answer here is 1 plus, sorry, I can't really tell you what the rest of the answer is yet. Okay, it's a way of leaving a hole so that your code actually compiles with no red squiggly underlines. There's no compiler error here, but you won't be able to evaluate this function because it's not well defined. Okay. What if we tried to apply du to not to root dir, which is a directory file, but to just a data file? Let's see what happens here if we put a data file. So we'll put, file.data and then a string name like slash and then some contents. No, this is a data file. It's not a directory file. So we'll just put, some contents in here like hello lean. Okay. And as our third argument, well, that's it. No, file.data, we need a file name like x.dat, okay, and contents of that file. And there we go. Okay. Oh, interesting. Check it out. Lean can actually evaluate this expression, okay, because du is defined for this case, where we're trying to count the number of files if we're just given a single data file, and that answer is 1. Okay, so Lean can evaluate the application of this function to an argument, or set of arguments, in this case an argument, a file, for which it has a defined case. But if we try to apply this function to this sort of case here, we get an error, and Lean says, no, sorry, you're trying to reduce a function that I don't know how to reduce. You're trying to reduce an expression, a function application expression that I don't know how to reduce. Okay, cool. So that's all I wanted to do on that example. Okay. So now we're going to do a couple of examples that that you haven't seen yet. Okay. So in our third example, we're going to define, a data type called tree of Booleans. You've already seen how to define a tree of strings. Defining a tree of Booleans or a tree of natural numbers or a tree of objects of some other kind should no longer be a problem. So a tree of Boolean values. And the data type definition is going to be very similar, right? So we'll call the tree that we're going to define, we'll call the type we're going to define here tree bool, tree underscore bool, okay? That's going to be our type name. And a tree of Booleans is either empty, okay? So it's either an empty tree of Booleans, or it's a non-empty tree of Booleans. So we'll just call that a node, okay? And that node will have a Boolean value, we'll call it v of type bool, and it will have two smaller trees, we'll call them L and R for left and right, of type tree bool. Okay, that's it. You should be at the point now where you're starting to say, okay, yeah, I get it. I've seen this before. So come on over here and let's go ahead and define a couple of, or at least one example of a tree of Boolean values. Let's define E as the empty tree of bool. So tree under bool dot empty. Okay, there's an empty tree of Booleans. And how about, let me, in a comment here, let's draw a tree of Booleans. True has two subtrees. I'll use left and right slashes here. And here, let's put false and another true here. And that's good enough, okay? That's good enough. So let's now represent that tree. So we'll define T to be this tree. So we need to represent this tree as a non-empty tree with true at its root. So we can't use the empty constructor. We need to use treebool.node. And so I'm going to put this on the next line down, treebool.node. And this constructor takes 3 arguments. It takes a Boolean value. So we'll put the Boolean value true at the top. In Lean, true is represented by the term TT. So there's that. And now we need 2 subtrees, one for the left subtree and one for the right subtree. This notion of using a pair of parentheses with an underscore, I do it all the time. It's really very helpful to me because now all I have to do is replace this underscore with another whole tree definition. Okay, so now I want to represent the left subtree. So that's really this tree. And what's not in my picture? Well, if this is a node subtree, it needs to have two children of its own. So we need some more trees down here. So there's a left child and a right child, and then this true tree has a left child and a right child. And yes, these will all be empty. So I'm just going to put E here. Having defined E to mean empty, I'll just put E's in this diagram at these points so I don't have to do a lot of typing. Okay. So there's really my tree. So now I have T defined to be a node to represent this element of the tree here with TT in the top node and two smaller trees, this one and this one. Now all I need to do is put expressions in these parentheses to represent each of these trees. So how do I represent the tree rooted at false? Well, it's not the empty tree, so it's just another one of these things. So it's got to be bool dot node with 3 arguments. Okay, I hope you're getting the idea here. I open this up, I put in space for the 3 arguments. There's a false, which in Lean is FF, and 2 subtrees. One I'll write like that, and the next one I'll write like that. Okay. Let's go ahead and do the right-hand tree at this point. So I've got, that's what's going to go here. Okay, it's not an empty tree, so I can't use tree_bool.empty. I have to use tree_bool.node. So this has to be tree under bool.node. Okay, and that takes 3 arguments. And one of them is going to be true, which is TT in Lean, for the true, and then 2 smaller trees. Because those are the arguments, a Boolean value, and a left and a right subtree, here and here. Okay, and so now I've got this, but I haven't represented these subtrees except I've left holes for them here. And of course, in each of these places, I just need the empty tree, but I've already got a symbol E defined to be treebool.empty, so I can just go ahead and put E here, E here, E here, and E here. And now I have a syntactically correct representation as a term in Lean of this tree, okay, represented as an object of my own, my own data type, my tree bool data type. Now, you should almost now, with your eyes closed, be able to write a procedure that counts up the number of non-empty nodes in this tree. So let's go ahead and do that. You call this count bool nodes. Okay, so we don't. Here, what's the type of this object? Well, it takes a tree of bools as an argument and returns that's \2 and returns \nat, a natural number, and it works by case analysis. And if the tree that you're given as an argument, if you apply count bool nodes to an empty tree, which is tree under bool.empty, the answer has got to be 0 because there are no Boolean values in an empty tree of Boolean values. Sorry, I'm struggling here a little bit with my paperwork. Excuse me. Otherwise, the tree's not empty, so it's got to be treebool.node applied to a number of arguments, a value, a left tree, and a right tree. And remember, we need to enclose these kinds of expressions in parentheses. In that case, the answer is, well, there's one Boolean value for v plus the number of, and here, let's bring this down onto this whole expression down onto the next line and indent it like that, plus the number of nodes in the left subtree. So that's this, count bool nodes L, plus, and let's go ahead and just put an underscore here to illustrate again how this is used. If we hover over this underscore, we see that what's defined in this context is v is a value of type bool, and L and T are themselves trees of Booleans. And so And count bool nodes is a function that can take a tree of Booleans and reduce it to a natural number. I called this V, L, and T. I guess I should have called it V, L, and R. Okay, it's not just any old tree, it's the right tree. And there we go. You saw the value of type checking, static type checking there. Eileen caught the error that I had made, and I immediately saw what I had done wrong. Okay, now how many Boolean values are in this tree? That's 3. Okay, and we can see right away that this is going to work. So count bool nodes applied to T, and you can just be sure that that's going to give you 3. So let's see what happens here. Let's look just in a little more depth. What kind of expression is this? Right, this is a function application expression in which a function given by its name, so here we've bound a name to a function from trees of Booleans to natural numbers. Okay, so to evaluate this expression, we first evaluate this name and get the definition of the function. Then here's the argument. We evaluate t and get this expression. Now we apply this function to this value, and how does it work? Well, we look up the definition of this function, and it has 2 cases. Remember, this is the argument that we've been given, and we do pattern matching. So we look at the top level term in the tree here, the constructor that was used to build it. Does it match with treebool.empty? No. Does it match with treebool.node? Yes, indeed it does. Treebool.node here matches with treebool.node here. As long as V matches with TT, L matches with this subtree, no matter how big it is, and R matches with the second subtree, no matter how big it is. So in the context in which V, L, and R are bound to TT, to this left subtree, and to this right subtree, we then can compute the answer. And the answer is it's 1 for the node that we're looking at, V, plus the number obtained by evaluating this function application expression. And this function application expression looks almost like the one that we started with here, except we're applying count bool nodes to a smaller tree, aren't we? The L subtree here is smaller than the big tree that we started off with. And that's the key to recursions eventually terminating. You keep applying the same function to smaller and smaller objects of type treebool, and eventually what are you going to reach? You're going to reach those E's, those empty nodes down at the bottom. Okay, so the first application of count bool nodes to T applies the definition of this function, given these 2 cases, to the tree T, matches the second constructor pattern, binds V, L, and R to TT and these 2 smaller trees. And the result in that context is 1 for the tree for the TT that we're looking at here, plus the result of counting up the number of nodes in this tree, plus the result of counting up the number of nodes in that tree, right? Each of these function application expressions also reduces to a natural number because count bool nodes takes a tree as an argument and returns a natural number. So here we're adding up 3 natural numbers, okay? 1 for the root of the tree, plus the number of nodes in the left tree, plus the number of nodes in the right tree, and you can see here that it works just fine. Cool. Okay, but now here's something more interesting. Suppose that we wanted to write a function called tree and. You probably remember from your Python and Java experience that Boolean expressions can include and operators and or operators, among others. How does AND work? Well, it takes two Boolean arguments and returns true if both of them are true, otherwise it returns false. But what if you have a whole tree of Boolean values? Okay? We'd like a function that returns true if all of them are true and false otherwise. So it returns false if at least one of the elements in the tree is false, otherwise it returns true. That's another way to say it. Okay, so let's define a function called tree and see how that would be defined. So again, it's going to take a tree of Booleans as an argument, but now it's not going to return a natural number, it's going to return a Boolean value. True if everything in the tree is true, otherwise false. Okay. Once again, there are going to be these two cases, right? They're the same cases. Either a tree is empty, so that's this case, or the tree is non-empty, in which case it contains a Boolean value, and a left subtree and a right subtree. So there's a really interesting question. What value should we return if the tree is empty? An empty tree is a tree, and we're defining a function that given any tree must return a bool. So we have to return a Boolean for the empty tree. So what's the right answer? Well, to get a sense of the right answer, it really helps to think about the non-empty case first. Okay, so let's think about the non-empty case first. So the idea here is we have a Boolean value v, and what we want to do is we want to return true if that value is true, and if the left tree contains all true values, and if the right tree contains all true values. So in Lean, the bool type is already defined for you. We'll actually look at it in detail later. And there's an operator, ampersand, ampersand, that implements the usual AND operator of languages like Python and Java. So we want to return true if v is true, and if the subtree L contains all trues. For that, we'll recursively apply tree AND to L. And if the right subtree contains all true objects. And I have an invalid expression error here because we haven't filled in what I should have put as a whole here. So there, now at least we have an expression that evaluates properly. So now what is the right value to return? I think our hand is forced for an empty tree. So suppose that we have a tree with just one Boolean value in it. Let's say it's true. And it has two empty trees as its children. We're going to compute the AND of true, and whatever we get from evaluating the left and the right subtrees. The left and the right subtrees, though, are empty. So if we return false for those trees and we AND true together with false and false, we're going to get false. Even though the tree has only true nodes in it, because there's only one true node in the whole tree. That is the tree. So we can't return false. We have to return true here. And that's the right answer. Okay? And that's the kind of reasoning that you're going to want to start to go through when you think about, what's the right answer for the base case of this kind of recursion, given the operator that we're using to combine our partial results. We're using an AND operator here to combine our partial results. And because we don't want the results for the empty subtrees to invalidate the result for all of the non-empty nodes in our tree, we actually have to return true here, because if we return even one false, it's going to turn the whole answer false every time. Okay, and every tree is either empty or contains empty subtrees at some level. So we would always get the answer false if we return false for the empty tree. So really we have to return true here. And now let's go over here and see what we get when we apply this function, count tree and, to our tree E, the empty tree. When we apply tree and to the empty tree, what should we get? True, exactly. And there's the right answer. What if we apply tree and to T? And before I show you the answer, go ahead and look at that tree. What's the answer going to be? It's going to be true and the result of evaluating this tree, which is going to return, well, it's going to return false, right? False and true is false. So this is going to be true and false and true. True and false is false. False and true is false. And so this is going to return false. And sure enough, it does. What if we changed this FF to a TT? Now this tree contains only trues, and so we get true here. I'm going to change that back to false. Okay. So as an exercise in your homework, I'm going to ask you to implement a tree OR operation. And what a tree OR operation will do is it will return false if every value in the tree is false, or true if there's at least one true. In fact, that's the better way to say it. Okay? Both ways are valid. So tree OR, think about OR in Java or Python. You know, what is true or true? True. What is true or false? True. What is false or true? True. What is false or false? False. You only get false if all of the arguments are false. So rather than just taking two arguments, our tree OR function takes a whole tree of Boolean arguments, and it returns false only if every element in the tree is false. Otherwise, it returns true. Okay. Now you're going to have to think about, and you're going to write this and you're going to test it. And you're going to test it thoroughly enough on enough different cases that you'll see if there's an error in your logic. And in particular, here's a little hint, you're going to have to think about, you know, what's the right answer for the empty tree. Okay, but I'm going to let you figure out the answer to that question. Okay, so that is the end of our sort of review and extension of the material that we have on trees and recursive functions. Well, it's almost the end. It's almost the end. You see in a couple of the preceding definitions here, tree bool, tree nat, tree string. Essentially, they're all the same. Essentially, all the same definition. Let's look at a tree of natural numbers, for example. Okay, we're not quite done yet. We're going to look at one more issue. So let's look at a tree of natural numbers represented by values of type nat in ling. Tree of natural numbers. Okay. So I've copied and pasted the definition of tree of bool, and now I'm going to change it into a tree of natural numbers. So I'm going to change the name here from tree bool to tree nat to represent the difference in the type of argument. Empty is, I'm perfectly happy with that as a constructor name, but now empty is a value of type tree nat. And now node, instead of taking a bool, takes a nat. And the left and right subtrees are now trees of nats, not trees of bools. Aha! I changed bool to nat here, bool to nat here, bool to nat here, bool to nat here. Otherwise, the two definitions are exactly the same. So let me copy and paste the previous definition inside of a comment here so you can compare these two. You have bool here, but nat here. You have bool here, but nat here. Bool here, but nat here. And bool here, but nat here. Now suppose I want a tree of strings. What do? I change this to string. 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 And now I have a data type for trees of strings. Now what if I want a tree of expressions? Assuming expression is a data type. Same thing. Copy and paste this definition and change every string to expression. At this point, I hope you're saying to yourself, Kevin, it seems like you're repeating yourself. And in fact, I am repeating myself. And what's the one thing we really hate to do as computer scientists? We hate to repeat ourselves. So when we're repeating ourselves almost exactly, but with certain systematic substitutions made in a piece of code, then we always jump to the possibility that we should only write the code once, but with a parameter. Okay, and the parameter here is the type of object in the tree, right? So here we have a Boolean object in our tree node. Here we have a natural number object in our tree node. Here we have a string object in our tree node. So what's the answer? You already know it from the last lecture. Polymorphism. We don't need to do this over and over and over again. What we can really do is define one polymorphic tree type, and it would go like this. Actually, you try it. Turn off the video at this point. Go back and look at the previous video. I mean, I strongly recommend that you do this, okay? I'm not there to watch you, but I'm telling you, for your own good, go ahead and do the work, okay? You don't have to. I can't tell whether you have or not, but go do the work, and it'll really help you a lot to see what's going on. Define a polymorphic tree type. Pause the video here, go have a look, give it a try, and if you get stuck, we'll do it together. Okay, see you in a minute. Okay, a minute has gone by. So we're going to define tree as a polymorphic type builder that takes a type as an argument. And in Lean, people use Greek letters like \alpha as type parameter names. You don't have to. You could use capital T here or something else. But if you want to be really cool and kind of like a mathy person, you know, learn to use Greek letters. Okay. So what this says is, and I'll put :type here. What this says is that if you apply this type constructor tree to a value of type, such as string or nat or bool, then you'll get a type. Tree applied to an argument of type will give you a type. Okay, so let's go above here and just remind ourselves, what's the type of nat? Yes, nat is a value of type. Here I require a value of type. So I could say tree nat, for example. What's the type of string? String is a type, so its type is big T type. So I could say tree string. You see the polymorphism here. I can build trees of objects of any type, okay, by applying the tree type builder to a type argument. What's the type of tree nat? That's a type, so I could build a tree of trees of natural numbers. A better way to do that, though, would be, can this possibly work? What's the type of tree nat? Oh, that's a type. Yeah. So this is a tree of values of type tree of nat. It's a tree of trees of natural numbers. Okay, so you can do a lot with this. Okay, so I'm going to delete that from here, and now we'll give the constructors for a tree. So empty is a value of type, and here we can leave off the alpha. Okay, so empty is a type, is a and here's how to think about it. Really, there's an implicit alpha here. Okay, so let me not go down that rat hole, but empty is a value of type tree of alpha. And what do you think the constructor for a non-empty tree looks like? Node takes some value v of type what? Of whatever type of element is in the tree, and that's called alpha. So there's the type parameter right there. So we have a node with a value of type alpha, whatever it is, followed by two smaller trees. So we'll call them again left and right, or just L and R to be kind of cryptic about it. And here we will say that left and right are trees. And here we actually need to do this, which is why I've been doing it all along. And I will declare that an object constructed in this way is in fact a tree of this type. And notice I don't need to put the alpha in either of these positions here. That's something that's you'll find a little bit confusing. You play around with it as you go and get comfortable with it. Okay, and now we can define a polymorphic function. You've already seen polymorphic functions that take a tree of objects of any type and return, for example, the number of non-empty nodes in that tree. So let's go ahead and define tree count. Okay, and the idea is that this function is going to take a tree of objects of some type alpha and return a natural number, the number of objects in that tree. But to make this work, we need to pass a parameter alpha of type as part of the definition of this function. Okay. So the type of function tree count is it's polymorphic. Tree count applied to a type, in other words, an expression like tree count nat or tree count bool or tree count string, is a function of type tree nat to nat, tree bool to nat, tree string to nat, so on and so forth. And here are the rules. If you give me tree.empty, I will give you back a 0, because that's how many objects of type alpha are in an empty tree. I've got an error here. What is it? If I leave that off, I have an error here. It says there's a missing case. I haven't given a definition for how this function operates when applied to a non-empty tree built by the tree node constructor with 3 arguments. So now we do that. Okay, put in parentheses, tree.node, a value v, a left tree and a right tree. And in that case, I return 1 for the current node containing the value v plus tree count L plus tree count R. And that adds up and returns to me the number of nodes in the overall tree. Okay. Pretty cool. So I will put as a comment here, polymorphic tree type. Okay. And over here, let's see how to use this definition. So let's take this tree T here and see what changes we make to it if we make it not a value of type tree bool, but just a value of type tree tree bool. Okay, so T currently is a value of type tree bool, right? We can check that by giving an explicit type here. I'm getting an error because the name is conflicts with the name T here, so I just use a tick mark to disambiguate the name. You can see T prime is of type tree bool, and here's the rest. Now we're going to change T prime to be not tree underscore bool, but tree space bool. This type builder applied to a type argument, bool. Okay. Now what happens here? This goes away. This goes away. This goes away. Well, why? What do we do when we get into a puzzle like this? Well, there's some error messages here. Okay, so what I tried to say is, the tree of Booleans, tree has an empty constructor, tree has a node constructor. That's the right constructor. Takes a value of type bool here. So that's right. What about this? Well, what does this error message say? Oh, type mismatch at application tree node FFE. Term E has type tree bool. Aha! Okay, we defined E above as of type tree underscore bool. That's not the right type for this. So what we need to say here is tree.empty. And here, tree.empty. And in the other places where E appears, we need to say tree.empty like this. And now we have a value of type tree of Booleans, okay, built using our polymorphic tree constructor. That's pretty cool. Now let's make a copy of this tree and turn it into a tree of gnats. Okay, change this to gnat. And now we have type errors here. And what's the type error here? Well, we're applying tree node to TT, which has type bool, but we've said that the elements of this tree should be of type gnat. Aha! So we can put a 3 here, a 4 here, and a 5 here, and that should take care of it for us. And of course, we have to change once again the name of this object so that it doesn't conflict. Pretty cool. Now we have this function down here, tree count, that counts up the number of nodes in a tree of any kind, of any type, with any type of objects inside of it. So let's evaluate the application of tree count. And I'm actually going to change the name of this function to tree count prime, okay? Because we're going to come back and improve it in just a second. But we're going to apply tree count. We're going to evaluate the application of tree count. Now we need to give some arguments. First, we need to give a type argument. Well, if we want to evaluate the application of this function to a tree of bools, then we need to say that alpha is bool, and now we need a tree of bools, like this one, T prime. And how many bools are in that tree? Well, it's 3. Okay, you can go count them yourself. If I want to evaluate the application of this same function, this polymorphic function, tree count prime to a tree of gnats, then I'd need to say we're going to apply tree count to a tree of gnats, so gnat is alpha, then tree gnat is the type of tree, and that's like this T double prime here. And that works just fine. If I tried to apply tree count gnat to T prime, it wouldn't work. What's the type error? Well, the term tree count gnat T prime, the term T prime has type tree bool, but it's expected to have type tree gnat because I've said gnat here. So the argument here is expected to be a tree of gnats. And now it is. Okay. Now, here's the interesting thing. Ling knows that T prime is a tree of bools. So it knows that, there's only one possible value, type value, that can go here. It's got to be bool. If I put gnat here, I'm going to have a type error. Okay, so if T prime is of type tree of bool, then this has to be bool. So in fact, Lean can figure out that has to be bool. And here we can use an underscore, it's a hole, and Lean actually fills the hole with the right value. Often when you use a hole, such as in our earlier code here, we used a hole here, and we got a little error message. It said, read the error message. I don't know how to synthesize the placeholder. Okay, placeholder is a synonym here for the hole, or the missing piece, and Lean is telling you, I don't know what to fill in there. I don't know what you want the rest of this expression to be. Okay, here, it has enough information based on the type of t prime to know what value has to go here. And in fact, of course, it could fill in this hole too. I'll just leave a nat there. So you don't actually have to explicitly provide these type arguments. Okay, but putting these underscores here is also a bit of a hassle. So I'm actually going to put the bool back in here, and I'm going to put the nat back in here. Okay, and I'm just going to copy and paste these couple of lines to here and replace these with underscores so you remember that Lean can actually infer, figure out what the values of these arguments need to be, what the value of the type argument needs to be, given the value, given the type of the tree argument, the second parameter can figure out what the value of the first parameter has to be. So you can use underscores here, and Lean will actually fill them in with the right answers for you. But there's an even slightly better solution in general, and that's to use, and pause the video right here, and stop and think about it. What's the term, what's the phrase that we want to use here? We want Lean to infer these type parameter values implicitly. We want not even to have to write underscores here, so we want Lean to use the construct known as implicit arguments. Okay, and the way that we're going to do that is we're going to write a slightly different function definition. We'll call it tree count without the tick mark in this case. And what we're going to do is what? How do we change this definition? We just replace the parentheses here with implicit arguments. And of course, we have to change the names of the recursively called functions here. And this tells Lean that it requires this type argument alpha, but don't make me write it out. Don't make me even put an underscore. Just figure out automatically and invisibly what the value of that argument has to be based on the type of the second argument of type tree alpha. If you know what the type tree alpha is, then you know what alpha is. If you know you're looking at a tree nat, then alpha has to be nat. If you're looking at a tree bool, then alpha has to be bool. If you're looking at a tree string, then alpha has to be string. Okay? And so with that in place, we can now see again the most beautiful sort of code, tree underscore count. Here now we're using this version rather than the previous version. We leave out the implicit type argument, and we can just we can do what looks like you're just applying this function to arguments of completely different types. And it gives the right answer in both cases. Here, you're applying tree count to an argument of type tree of bool. Here, you're applying tree count to an argument of type tree of nat, and it just works like a charm. Okay, under the hood, Lean actually knows that this function requires two arguments, the first being a type, the second being a tree of objects of that type. But given that second argument, it can figure out what the first one has to be. So it allows you not to have to say anything about it at all, and it just infers it silently. And it allows you to write really quite beautiful code. I mean, this is really something that in a strongly and statically typed language in which functions have very, very precise types, that you can write code where you're applying the same function to objects of different types, or at least it looks like that. Okay, so at the beginning of this lecture, I promised that we would move on to expression trees, and I think probably this is a long enough piece of video that I'm going to stop it here, and I'll pick up in the next video with expression trees, and we'll actually make a major advance, and we'll get to the point where we can define a kind of a programming language that you begin to recognize as something that could be quite useful, a language of arithmetic expressions with a syntax, a semantics, and an evaluator to reduce arbitrarily complex arithmetic expressions to the numbers, to the values that they represent. We're going to implement, essentially a kind of a language of arithmetic expressions in a calculator for evaluating them automatically.